And now we continue with our lesson on sampling and measurement. So now we look at our paper tape sampler, and this particular instrument is used to measure the soiling effects of particulate matter in our air. Alright, so it's constructed of a pump. There's also a filtering mechanism and also a timing device. So the principles by which this works, as you can see, it draws air through a strip of filter paper at a specific rate. So this would be our paper. This would be the roll, which is the source of our paper, and then you have a take-up spool. So the paper is going to roll in this direction and it would be taken up here in this spool. This pump is what drives the entire process, and here we see the conduit through which the air comes in. So as the paper passes this particular point, it would be released onto the paper, and therefore you would be looking to determine the amount of soiling that takes place on the paper at a specified time, in a specified time period. So this is how the paper tape sampler equipment would work. Okay, then we also have our dust fall bucket. Okay, and as it says, what you have is an open mouth container made of glass, polyethylene, or some other type of inert material. So these are the materials that it could possibly be made from. That's our container. So this container collects settleable atmospheric particulate matter that would be in the air. So you're talking about really the coarser, heavier material that would drop as a result of the weight of gravity. What is collected is therefore weighed, and results would be reported in milligrams per square centimeter over a month's period. So you'd be looking at each month how much settleable particulate material was acquired. Alright, now this particular instrument is really of limited value as an air monitoring tool, because it can only really measure particulate materials in the air over localized areas. It doesn't really represent patterns over large geographic areas. Okay, this is what the instrument might look like. So this here is our container. Notice the schematic shows you the container is mounted upon a metal stand that's approximately 1.2 meters high. Okay, and it's a very simple instrument. It just allows the heavier material to naturally fall into the funnel and be deposited in the container. Our next instrument for measurement, this is called our high volume sampler. So this is used over a 24-hour continuous measurement. So it's measuring continuously over a 24-hour period, and it measures both PM 2.5 as well as PM 10, fine and coarse, for both indoor and outdoor sampling. Okay, so remember, when you're talking about air quality, those are some of the issues you need to pay attention to. Not only the size of the particulate matter, but there's air quality out in the natural environment, which is outdoor sampling, and then there's air quality indoors, and each one can be affected by different issues and different conditions. Now the high volume sampler, the rate of air through the filter is measured in liters per minute. So this is how it is measured, and it features a high-speed motor with durable weather shelter. So let's see what this looks like. So this is essentially what the equipment looks like. This is the shelter. All right, so everything is properly housed inside of here. You have your pump, an exhaust here, flow meter, and this is where the filter takes place. This is where it traps the the particulate matter. Alright, and if you look here, you see the different monitoring instruments. Everything is digital on this machine here. Alright, so that's your high volume sampler. Now we're going to look at gas sampling. So these are three different instruments that can be used for gas sampling. One is our nitrogen oxide chemiluminescence analyzer, our ozone chemiluminescence analyzer, and our carbon monoxide infrared analyzer. So the first one we're looking at is our nitrogen oxide chemiluminescence analyzer. All right, so from your glossary, you should recall that chemiluminescence literally means a chemical reaction that produces light. Okay, so when you have a nitric oxide molecule that reacts with ozone, right, you have a chemical reaction taking place. So it's now oxidized, so it's now nitrogen dioxide. It's now in an excited state because you have that reaction. What happens is a small fraction of the molecules in that excited state, it decays and breaks down by emitting a photon in the near infrared portion of the spectrum. So in other words, it's emitted, as it breaks down, it's emitting light. So as chemiluminescence defines, it produces light. That is, the light in the near infrared range is emitted. So that chemical reaction produces light. Chemiluminescence has long been recognized as the best practical analytical method for nitrogen oxide detection. Okay, or nitric oxide detection. So the amount of light that is produced is in proportion to the amount of nitric oxide and the amount of the particular gas pollutant in the sample of air. Okay, so what happens is you will mix a gas sample. This is how it works. You mix the gas sample with ozone and measure the amount of light that is emitted. The amount of light represents the concentration of the nitric oxide in the sample that you've taken. How does the analyzer work? Right, so the sensors, the chemiluminescent sensors, they are most appropriate for use in the stratospheric application. So those are the higher levels of the atmosphere. It's specifically in the estimation of ozone and nitrogen oxide concentrations. Right. So inside a chemical reactor, a chemiluminescent sensor is placed along a line where the airflow to be analyzed is provided by a pneumatic pump. So the pneumatic pump sucks in the air and releases it along a line that passes the sensor, the chemical reactor. Right, so the luminescent light produced by the sensor that the air passes is modified and registered by an electronic unit. So the air is sucked in from this is how they get the sample of air. It's sucked in from the atmosphere, directed by the pump, past the sensor. The sensor light modifies according to the amount of ozone and nitrogen oxide in the air sample, and this is registered by the electronic unit to give out a reading. This is an example of what this instrument would look like. As you could see, it looks like it's fairly complex. Most of the parts are hidden inside of this container, and you see a digital reading could be given out on this computer screen. Right. And lastly, we have our carbon monoxide infrared analyzer, IR meaning infrared. Okay, so this is a non-dispersive infrared detector. These are industry standard methods for measuring concentrations of carbon oxides. Okay, so the gas in a sample, right? So the gas in a sample will absorb some of the infrared light at a particular frequency or particular energy level. Okay, by shining the infrared beam through the sample and measuring the amount of infrared absorbed by the particular gas, right? So the carbon gas, however amount of carbon gas is in there, it will, the greater the concentration of the gas is, the greater the amount of absorption of the infrared light would occur, right? And this in turn would now allow you to be able to measure the amount of carbon monoxide or carbon dioxide in your sample. So in this case, your interest is in the amount of infrared light absorbed. And this here is an example of what a schematic of what the instrument might look like. So here you have your motor, and this is where your infrared light is. You have your gas inlet, it comes in here, it comes out here, and you have your detectors here. So as a gas passes here by your light source, it will absorb a certain amount of gas, a certain amount of light, sorry. It continues, it passes out near the detector, and the detector will make the calculation as to how much of the gas was contained in the sample. So at this point, I would like to thank you for joining me for today's lesson. If you can kindly proceed to this week's activity. Thank you very much.